let's do this. We're going to do 2 of these. Quick review, real quick review. And cosine x plus y. Now let's just all do this together. This should, well, whoever coming back from Christmas break, it might be hard. But what is this? How could I rewrite sine something plus something? What would it be?
Sine of x.
Let's just do the structure first. It's what?
Sine, cosine, sine, cosine.
There you go. Sine, cosine, sine, cosine. Okay, that's the form. Now let's do the SIG in here. Plus, because sine is the same. Right, so if it's plus inside, it's plus right there. Now, what do we do?
X, y, y, x.
X, y,
Y, x.
y, x. Right. Okay. Otherwise, it would be really simple. It would just always be like sine, cosine. There are 2 of them. Okay, anyway. Okay, now cosine x plus y. What's that form first?
Cosine, cosine, sine.
Cosine, cosine.
Yeah,
Cos. Sine, sine.
Minus.
And minus between, because it's the opposite with cosine. And so now what? I guess it doesn't matter, right? Like, it's the same. But yeah, we could do x, y, x, y. And if you prefer, so that it looks nice and symmetric, you could go yx, so that follows the same form. You could also write these in opposite order. Well, write these in opposite order, but who cares, right? This is the way I like to do it. Now, I want to do something. Check this out. This is what we're talking about today. Watch what happens when I do this. Now, we've proved, well, your book proves beyond the shadow of a doubt, and we did a very suggestive proof, that this works for any 2 numbers, x and y. That no matter what x is and no matter what y is, this is true. And we're at a point, I think, where we believe that. So it should also be true that if, instead of a y here, if I put a z, if I put x plus z, I'd put z and z. But if I put x plus x, I would have that right there. Right? But what is x plus x? What's the easier way of writing x plus x?
2x.
Sine of 2x. Okay, so instead of x plus x, if we have double whatever x is, maybe x is an angle, maybe it's pi over 4. Then when you double it, you would have pi over 2, right? Or whatever. Then this should work. But check this out. This thing's the same as that thing, isn't it?
Oh, yeah.
Sine x cosine x is the same thing as sine x cosine. So how many of them do we have? 2. So we could rewrite this as that equals 2 sine x cosine x. And this is what we call a double angle formula. So that sine 2x is equal to 2 sine x cosine x. Now let's do the same trick and see what we can figure out here. Here and here. So same trick. If instead of x plus y I said x plus x, well, we would have an x here and an x here. And this would be the same thing as cosine 2x. And what's that?
Cosine squared.
That's cosine squared. So cosine squared x minus, what's that?
Sine squared.
Sine squared x.
Wait, no.
That is not 1. If it were plus, it would be 1. And so now when you have a minus between them, it's no longer 1, it's now cosine 2x. But check this out. This is where it gets cool. This is one of the formulas here. But since, like you said, it is true that cosine squared plus sine squared is equal to 1, we could start manipulating this stuff. And we could say, well, hold up. Cosine squared is equal to 1 minus sine squared. And so I could replace that right here. And I want to have this nice and neat, so I'm going to do this like down here. So instead of cosine squared x minus sine squared x, we could have that as 1 minus sine squared. And so then that's 1 minus sine squared, that's 1 minus 2 sine squared. So this is the same thing as 1 minus 2 sine squared x. Or we could have played the opposite game. where instead of getting cosine by itself, I could have gotten sine squared by itself. I have 1 minus cosine squared. And then I could substitute that in here, and I would have cosine squared minus, now it's 1 minus cosine squared, 1 minus cosine squared. So that's cosine squared minus 1. A minus minus is a plus. So that's the same as 2 cosine squared minus 1. So this is also equal to 2 cosine squared minus 1. And so, there's a bunch of different ways we could write these guys. Kind of cool, huh? And it's like, all right, why is that important? Well, I mean, of course, we'll see an example in just a minute why you might want to calculate that. And I guess we'll just continue on, and I will explain to you why some of these are so important to commit to memory. But the cool thing, now remember I said you want to commit these to memory. And you could see it doesn't take long. Like if you could just, after having written this down a couple times, it doesn't take long to go, wait, what was the double angle formula for sine? Well, if you have this in your head, you've committed this to memory. It shouldn't be hard to remember. Oh yeah, that's right. Sine 2x is x plus x, and so you'd have sine cosine. Oh, it's the one that doubles when you put them together. Yeah. And then with cosine, you have this in your head, and you go, oh right, it's cosine, cosine, sine, sine. Oh right, it's the cosine squared, sine squared one. And so the thing is, what I said, like commit this to memory, and then it's not hard to derive these guys at all. So anyway. Now, we did sine, we did cosine. What are we missing? Tangent. So let's see if we could figure out what tan 2x is. So tan 2x is the same thing as what over what?
Sine of 2x over cosine.
Yeah, whatever goes in there has to go in there. Okay, so now let's just take them. So 2 sine cosine on the top. Now we could choose from any of the three, and I'm just going to choose the first one. So this is, there you go, okay? Could be done if we were so inclined. Well, we could write this in a bunch of different ways, actually, because, well, I could multiply or divide the top and the bottom by whatever I want, and so, and there's a bunch of different ways we could do this. I could do this with sine. I'm going to do it with, actually, cosine here. I'm going to go 1 over cosine squared on the top and the bottom. Why? Well, because this is the way that your book has it. So I want to derive the formulas that are in your book here. And so if cosine squared divides that guy out, I'm left with a 2, a sine, and then a 1 over cosine, right? But what's sine over cosine?
Tangent.
That's just tangent. So that's the same thing as 2 tan. 2x or 1x? I didn't write it here explicitly because I'm cutting corners, right? But in order for that to cancel, it's got to be 1x, right? So,
Yeah.
tan x. Now on the bottom, this guy jumps over, kills that guy, and we have 1 minus a sine squared over a cosine squared, which is what?
Tan squared.
Tan squared. And this is what's in your book right there. And there's other ways to write it. Like, I mean, as you've seen, at this point in this class, you should know that there's probably 1,000 different ways of writing this, right? We could write that as 2 over cotan minus 1 over cotan squared, and from there we could get a bunch of different things. We could turn tangent squared into secant squared and all kinds of stuff, right? But this is that's a nice one to know. As far as committing to memory, now we've entered into what I referred to as formula hell, right? Like we are getting into, we're just going to learn formula after formula after formula. And in the real world, what you're going to do is, you're going to look in the back of your book, and it has them all right here, okay? Or you go, oh, what was that one? And you get on Wikipedia real quick, and you go to trig identities, and you scroll down, and you go, yeah, that one right there. That's what's going to happen. However, there are a few that you will want to commit to memory. The addition and subtraction formulas, right? And then ones that we're about to derive here. And I say, like, these will be very, very important. They're going to show up all the time in your future mathematical endeavors, but they're easy to get from these. And now that you've seen that that these exist, you could probably go, wait a minute, hold up. Cosine was the one that went cosine, cosine, sine, sine. Oh, so that's the cosine squared, sine squared, and so on and so forth. But there's one we're about to do that you absolutely 100% want to commit to memory. Okay, check this out. So, okay, I'm going to get rid of this stuff up here. So this is how we derived it. Not too concerned with it right now. Ugh. Alright. Now. And those are nice. This is what we want to see right now. This one is so useful. Because, like, check this out. Cosine 2x is equal to this. So I'm going to go ahead and write it out. Cosine 2x. 1 minus 2 sine squared x. On the other hand, it's also equal to 2 cosine squared minus 1. Right? Yes. Okay, that works. Check this out. We're about to get one of the most useful things. And by useful, I mean when you take calculus, this will be one of the most useful things you could possibly have locked in your head.
Oh, because you can set them equal.
Nope.
Oh.
No, something else that we're about to do. So, watch this. I don't like negatives, and I want an expression involving sine squared. I don't like negatives, so what I'm going to do, I'm going to take him to that side and bring him to this side. I'm going to do that in one step. Okay, so I'm going to add the 2 sine squared over here. And I'm going to bring the cosine 2x over here. Is anybody mystified by that? Everybody following me with that one? Okay, check this out. Divide everybody by 2. 1/2 minus, and the way I like to do it is 1/2 cosine 2x. Now what you'll see in your book, if you look this up, and in every book, what you're going to see is it will be written like this. It's the same thing, right? Like, we just divide the entire thing by 2 and you get this. And that's cool, and it's probably not going to trip you up in the future. But this way, I'm telling you, for calculus, when you take calculus, if you have this locked in your head like this is another one of those that you will want to memorize for the rest of your life. This one and another one that we're going to derive that's just like it are so useful. I can't stress to you just how useful they are. And to have it memorized like this, it's slightly more helpful than having it memorized like this. Like that's which one you prefer, whatever. I find it that this makes the next calculations that you're about to do when you take calculus, this makes it a little bit easier than having it like this, slightly. I mean, there's not really that much of a payoff between these two. I just prefer it this way. It's a bit more straightforward. That's how I have it locked in my head. Now, let's do the same thing with the cosine. Okay, so we want the cosine squared by itself. So how about I'll add 1 over here, and I get 1 plus cosine 2x is equal to 2 cosine squared x. Dividing everybody by 2 gives me cosine squared, and I'm sorry, I'm going to flip the sides here, just so we can see this nice symmetry. Dividing by 2, we get the 1/2. Dividing by 2, the only difference is you have a plus 1/2. Everybody follow that, check that, and make sure I did that right, because I did flip the sides of the equation.
Yeah.
Okay, it's correct, okay. Okay, and so you see the difference between cosine squared and sine squared is simply if there's a plus or a minus between these two things. And you'll notice that if you add them together, cosine squared plus sine squared These guys cancel out, and all you have is a half plus a half.
Oh.
A half plus a half is 1. It's consistent with everything we've talked about up until now. But these, I don't think it calls them this in your book, but this is what is called elsewhere a power reduction formula. You have a power of a trig function, and you could reduce the power here. So you have something squared, you could reduce it to a first power cosine. You have something squared, you could reduce it down to a first power cosine. And that's what makes this so useful in calculus. Because you're going to do something called integration. And if you try to integrate something like this, it's like an operation, right? Like you want to do something to that function. Good luck. Like you'll sit there for a day trying to figure out how to do it. But this turns out to be super trivial to integrate. And the thing is, you end up with sines and cosines, so all kinds of powers. And if you could reduce them down to their first power, then what you're about to do, this integration thing that I'm telling you about, becomes trivial. It's like you could do it in your sleep. And so this is a very useful trick moving forward. And so I suggest that along with the addition and subtraction formulas, you commit these to memory. This would just be good to have for the rest of your life. Now, okay, so let's do an example. Now, the way I say it, and the way you're going to see it on a quiz, is I'm going to say, reduce this to first power cosines. Your book says, express in terms of the cosine function with exponent 1. It means exactly the same thing. But this is number 32. And it tells you to do this. And I think it's 2x. 2x? 2x. Okay. Now you'll notice that this right here is not to the fourth power. And you might think, like you might just naively go, oh, well, I could reduce it by half by doing this. It's just 1/2 plus 1/2 cosine squared something. That's not, no, it doesn't work. We don't have a formula for this guy. We have a formula for if it's squared.
We can reduce it to like cosine squared of 2x times cosine squared of 2x.
Yes, exactly. And so you could write it as cosine squared 2x times cosine squared 2x, or you could write it as cosine squared 2x squared, right? I mean, either way you want to do it, it means the same thing, right? In fact, I actually like it better to do it that way. Let's do it that way, because like, then what we're about to do will look a bit nicer. So yeah. Everybody buy that. Everybody with me on that, right? That something to the fourth power is just something to the second power times that thing to the second power. That's what that means. Because remember, all of this that we're talking about, all of this like cosine squared x, that just means you take cosine x and multiply it by itself, right? That's what that means. And so, yeah, okay. Anyway, ditto with fourth power. But now, okay, and this is probably going to help us if we do this. Because as you can see, when we move over into this area, there's addition. And if you don't have your parentheses, you might just mess all of this up like really bad. So I'm going to suggest you use some parentheses. And so now, here's the thing. That's the formula for cosine x. This is cosine 2x. So what do we need to do here? Like, what should this be?
1/2 plus 1/2 cosine 2x. Just times itself, right?
Let's think about it this way.
1 minus sine.
Let's do this. Whatever this is that right there. Now in here we have, instead of theta, we have 2x. So if I replace this with 2x, what happens to it?
4.
Yeah, and so the way I have this in my head when I see these formulas here is that you just take whatever you originally had here and double it. So my original thing is 2x. If I double it, I get 4x. So this is 1/2 plus 1/2 cosine 4x. So a 2 may not show up in your thing when you're doing this, right? Like if this were a 3x, then this would come out to be a 6x, right? The idea is that you'll notice you bring this down by you bring the power down by a factor of 2. You bring what's inside up by a factor of 2. So that's another way of thinking about it, right? Reducing by a power of 2, so you have to increase the inside by a power of 2. Or power of 2, a factor of 2. You're multiplying by 2. So that's 1/2 plus 1/2 cosine 4x. Now, technically, you might think, well, I'm done because I've reduced it down, and that's a first power cosine. That's a first power cosine. I'm done, right? Well, no, and I'm going to tell you you're not. And the reason why you're not is if you go to integrate this, like when you go to take calculus, you'll see what all this is prepping you for calculus. All these problems right here is really prepping you for calculus, because if you try to integrate this, you'll spend a month trying to work it out. If you try to integrate this, you'll still spend a month trying to work it out. You're not going to be able to get anywhere. The idea is, if you could get what you're about to integrate, that'll all make sense soon. But what you're about to integrate, if you have multiplication in there, if you have things multiplied by each other, your life gets 1,000,000 times harder. But if you could turn everything into just addition and subtraction, so if you could have just a bunch of terms laid out, then what you're about to integrate gets really, really easy, usually. It's much easier than trying to integrate something times something. And so, for the purpose of these problems in your book, they're training you for what you're about to do in calculus. And this is not going to help you. So what they mean is to continue on.
To multiply it.
So let's multiply it out. What do I get?
1/4.
1/4. Outer gives me
1/4
quarter cosine. Do I get the same thing here?
Yes.
So a quarter cosine
So 1/2.
plus a quarter cosine is a half. What? Cosine what?
4x.
4x. Then last gives me what?
1/4 cosine squared.
There we go. 1/4 cosine
quadratic.
squared 4x. It is a quadratic. But again, they're not prepping you to solve this for something. Unless, if it did say this equals 5, then you could, well, it wouldn't. This equals a half. Then you'd have, and that would be great, and you could do that, and we'd be done. The idea is this question is prepping you for calculus, and at this point, if you try to integrate this, you're screwed. If you try to integrate this, not going to happen. Not going to happen. Still not going to happen because that guy's there. And so now we need to go another step and say, we got to use our reduction formula again because this is not a first power cosine. And so I'm going to do this the long way. I'm going to write everybody out. A quarter, half cosine 4x plus a quarter, big parentheses. Because that's right. That's a quarter times something. That something is that. So let's use that. Tell me what to write.
1/2 plus 1/2 cosine of 8.
8x. And so yeah, you're again reducing the power. You got to up the input by a factor of 2. And so okay, this jumps over. Now technically we're done. Although it doesn't look very nice. And in calculus, it's going to be much better if you have everything just something plus something plus something, or minuses, whatever. It's going to help you out a lot. And so, let's just do it. Let's multiply that guy out first, and then we'll finish this up. Cosine 4x. Okay, so this jumps over and gives me what?
1/8.
And that jumps over and gives me...
1/8.
Now, can we combine any terms?
The 1/8 and the 1/4.
They give me a total of how many whats?
4/8.
Wait, no.
2/8. Yeah, 4/8.
No, wait.
2 eighths.
Oh no, sorry.
Plus an eighth.
It's 3/8.
3 eighths. There we go. Okay.
Yeah,
Plus
yeah.
a half cosine 4x plus 1/8 cosine 8x. I'm telling you, you'll see when you take integral calculus, you go to take an integral of this, or you go to integrate this. Good luck. You'll spend days trying to figure out how to do it. But then you go, hold up. And you reduce this down like that, and you could do this in a matter of probably 5 seconds, if that. If you're good, you could do it in 2. So this is very useful. I cannot stress to you how useful this is, and you're going to see it everywhere when you take calc and beyond. It's going to show up everywhere. So these are 2 that I suggest committing to memory, because this type of thing shows up a lot. You'll definitely be quizzed on something like this. You definitely, I will tell you to reduce this to first power cosines. And this is what I mean, that you get it all something plus something plus something. There's no multiplication or anything involved. So I don't want any confusion when on a quiz I say reduce to first power cosines. This is what I'm looking for. And it's so that when you do calculus, we don't have to spend forever going over it. Like, you just remember, oh yeah, we did that, we're good to go. So, okay. Okay, so now check this out. Did I want to do it? I did want to do it that way. So just again, we're in formula hell. Like, we're just gonna go over formula after formula. Can I get rid of this?
Yeah.
We got that. Okay. Okay. Continuing on. Remember, this all came from the addition formula? Like, we're going to just continue on and just keep deriving stuff. And it all comes from the addition formula, which we proved, at least we proved the acute case by pictures. And we're not doing that with anything else, right? We're like, everything we've done after that has just been manipulating symbols. And so all of this really comes from the addition formula, and we're going to continue on. Okay, I did it over here. So, this is true. What if, instead of theta, what if I said, let's let theta equal, say, x over 2. And I plug that in. What I have here? Well, theta would just be x over 2.
And then just add.
Yeah, because this would be 2 times whatever theta is. X over 2. The 2's would cancel, and I'd just be left with an x. Okay. I mean, we don't really need to do this to do what we're about to do. It's just, this is how you'll see it most places, especially in your book, on Wikipedia. This is how it will be presented, and so this is why it looks this way. Now, I could take a square root of both sides. Right? Like, and if I take a square root of something squared, the thing just pops out. But now when I do that, I'm going to get a plus or a minus. Right? 1/2 plus 1/2 cosine x goes cos x. Okay? We're going to talk about that plus or minus in just a second. I'm just going to let that hang there for a minute. But, yeah, we're going to let that hang there for a minute. Ditto over here, right? So it's not a 1. Okay? We could say, well, hold on. If I replace both of these x's with x's over 2, right? X over 2. I would have an x over 2 right here. Here I would have an x over 2. And so the 2's would cancel, and lo and behold, yeah, we're back in the same place here. And I could take a square root of both sides, and I would have sine of x over 2 is equal to, oops, the square root of, plus or minus the square root of 1/2 minus 1/2 cosine x. This could also be useful in calculus. Like, if you're trying to integrate this, good luck. But then you go, that's that. And so, yeah, that's cool. But anyway, But you won't see that very often. I mean, that's these are the ones you want to remember. Anyway, okay, so I said hang on to that plus or minus for a minute. Now, I remember, in the back of my book, when I was taking this class, my professor told me to rewrite what's back here. This is what's in the back of the book. It's like this one, it's U's instead of X's. And he said, instead of doing that, it should be an absolute value sign right here. Instead of a plus or minus, you would have the positive square root and the absolute value sign.
Which is kind of the same.
It means the same thing, right? But technically that is a better way of doing it. And because it's like, I don't know about you, but when I see a plus or minus, it's like, okay, now I have two answers. Well, if you plug something in there, you're not going to get two answers, right? It's just, we're just saying, so it'd be much better if we just do an example here. So here's an example. We want to compute cosine of pi over 12. Now we did something like this when we were working with the addition and subtraction formulas. If you could find something minus something that equals pi over 12. And I think we did, it was something like pi over 3 minus pi over 4, maybe that works. I'm not sure. I actually think that might work, right? But we have a much more direct way of doing that now. We could say, well, hold up. Is that half of some angle?
Pi over 6.
Pi over 6. Do we know pi over 6?
Yeah.
Yeah, so in other words, what I'm saying is it's like if theta is equal to pi over 6, then theta over 2 is equal to pi over 12. Or rather, I guess we're using x's here. So if I let x be pi over 6, then x over 2 is equal to pi over 12. Well, that's the thing I want, right?
Yeah.
And so I could say, well, then if that's half, yeah. And so I could just use this formula here and say, okay, I have plus or minus the square root of 1/2 plus 1/2 cosine. Now I just double the angle, right? And that's another way of looking at this. Because remember where this came from, right? We were just doubling these angles. It's the same kind of relationship here. They just like to present it this way. But the way I think about it in my head is I know where this thing comes from, and so I think whatever this is has to be double that amount. Whatever. These are, by the way, called the half angle formulas, and the other ones are called the double angle formulas. It's the same thing. It really bugs me that they have different names. It's like, you see why it's the same thing. It comes from the same thing. It's just, you just have to remember which one's double which, you know? And in both cases, there's something doubled. Why they call this one the half, it just drives me nuts. It's like, oh, it could have just, like, just think about doubling the angle. It's, I don't know, whatever. So, okay. Do we know what cosine pi over 6 is?
It's root 3 over 2.
I think so. There's a root 3. Here's a 2. Here's a 1. This one's pi over 6. Cosine pi over 6 should be root 3 over 2. So here we go. String along this plus or minus. 1/2 plus 1/2 times root 3 over 2. Which is the same thing as 1/2 plus, so that's root 3 over 4. Why don't I get a common denominator?
So
2/4.
2/4. So that's the same thing as plus or minus the square root of 2 plus root 3 all over 4. But this is a radical, right? So the top and the bottom, I could just do like this. This is plus or minus that. And so we have the 2 plus root 3, 4, which is just plus or minus, I'll do it down here, plus or minus the square root of 2 plus root 3 all over 2. So is it plus or minus? How do we know? How come?
Oh, it can't be a minus.
Why not?
Oh, wait. Yeah, it can.
Yeah, why not? Tell me.
Well, the square root of something can't equal negative. But
Well, yeah, but that's it could. I mean, a squared. It could be negative. How could we figure this out? And the key is right there. Let's think about what cosine looks like. Cosine does this thing. What's this value right here? And the x-axis, what's that value?
pi
Pi
over
over
2.
2.
Pi over 2. So where does pi over 12 live?
Less than that.
Less than that. Not quite at 0, right? He's not all the way there. He's somewhere in here. Is cosine positive or negative there?
Positive.
Positive. So in other words, if you plug in pi over 12 into cosine, you will get out some positive number. That's how you deal with the plus and the minus. Another way of doing this is instead of plus and minus, you take the sign, that's SIG, that's the abbreviation for it. You take the sign of whatever this is. I'm sorry, this is going to be all confusing. Don't write this down. You take that's what I mean. So if it's if this number is positive, then it's positive. If it's negative, then it's negative. And that's what this is. But you have to look back at this thing right here and just use your brain and say, well, wait a minute. Should this be a positive or a negative number? Well, is cosine positive or negative at pi over 12? So then you have to use your brain and go, well, pi over 12 lives here. The output of cosine will be positive there, right? Another thing you could do is look at the unit circle and say, well, if this is pi over 6 and this is 0, pi over 12 is somewhere between them. Cosine corresponds to the x value. The x value is positive there, so I'm going to take the positive one. And so on and so forth. So that's how that's what I mean by like just that thing. There's a bit more going on with the plus and the minus. You actually have to use your brain and say, well, hold up. Where does this thing live? Is my function, in this case it's cosine, it could have been sine. I could have said sine with all of this. And in the case of sine, it would still be positive there. But that's the idea. Cool. Questions on that? All right.
Can you define integration?
Can I what now?
Define integration? Because we've been talking about it, but I don't know. What
Okay, down and dirty, like the just down and dirty way of thinking about integration is as the area under a curve, or the signed area under a curve. So for instance, you have some function. Say it looks like this. Right there. Let's say this is f of x. And we have some interval. Maybe it's from, say, 1 up to 2. Well, this area right here, the area between the curve and the x-axis, right there, that area, call it A. That area can be written as the integral from 1 to 2 of this function f. Don't worry about what that dx means right now. But that's what that means right there. That's one way of thinking about it. There's another way of thinking about it. And this is like the fundamental theorem of calculus, is that this is connected to something else that you'll learn when you take calculus. But that's what that means. That's what that is. But it's also the signed area of the curve. So let's say this is 4. If we go from 1 to 4, then we're talking about all of this area here and all of this area. And we would think about this as a negative area. So if all of this area here came out to be, say, 5, and that area right there came out to be 1, then altogether it would be 5, because it's positive, minus the 1 down here. So that's what... But in order to do that, there's this connection to something else in calculus that you learn, and you say, and you will learn in calculus that there's another way of doing this. That you could estimate this. There's a bunch of different ways of estimating this. Computers do that. They take fine little bits and take values and say, well, if this is about this high, then I could pretend that that's a rectangle, and I could go here and say, well, if that's a rectangle, and I could go here and say, if that's a rectangle, and then you have a bunch of heights and a bunch of distances. And then you could say, well, I could just add up all these little areas, and I'll get an approximation of it. And then, yeah, and so that's how that's how many computers do that. But there's another way of doing it and computing it exactly. And that's with the fundamental theorem of calculus. This thing is connected to something else that you learn. And there's a way you can manipulate this function to find it exactly. And so, if you see something like this, cosine squared x, and you want to take the integral of that, good luck. Good luck. You'll just sit there all night. But then you go, oh, wait, I can replace it with that. And you do, and it's, got it. You got the exact value like that. So, yeah. That's worth talking about. Thanks for the question. Any other questions? Any questions before we go on? Okay. So now we have a formula for, these are the half angles, right? We have, oops, x, right? We have these guys. We have sine, we have cosine. What are we missing? Tangent, right? Of course we're missing tangent. So here's the thing. I mean, we could, if I were so inclined, I could just divide that one by that one, and we'd have the square root of blah, 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 blah. Or, let's think about where this came from. We did all this manipulation, and then finally at the last stage of the game, we took a square root. Let's do the same thing with tangent. And what I'm going to do, this is going to be one of those few times where I'm going to say, hi Effie, this is going to be one of those few times where it will be useful to say, you know what, let's rewrite this as instead of a half minus a half cosine, let's write it as 1 minus cosine all over 2. Everybody see what I did there? Yeah. Right. I'm going to do the same thing here, where this, wow, okay, where this is all over 2, so we have the 1 plus cosine all over 2. And so then, tangent squared of something, and why don't we call it x over 2, should just be sine squared of that thing over cosine squared of that thing. And so now we have sine squared is this guy, so 1 minus cosine all over 2 divided by 1 plus cosine all over 2. But then, yeah, and so that's the nice thing, right? Like this flips, the 2's cancel, and I'm just left with this in the numerator and this in the denominator. Everybody got that?
That one
right.
looks much nicer.
It does, right? It looks much, much nicer. And so now I can take a square root. Okay, I'm going to do this first, then take a square. We would have ended up with the same thing the other way. But there's an interesting technical thing that's about to happen. Now that I've done this, I'm going to take a square root of both sides and get tan x over 2 is equal to, I took a square root, so I have to have this plus minus, 1 minus cosine x over 1 plus cosine x. That's one way of doing it. But check this out. So that's one way I could have done it. That's one formula we could have for that. But watch this. What if I didn't do that? What if I said here, wait a second, hold up. I can multiply the top and the bottom by the same thing. And in one case I could do this with 1 minus cosine x. And what does that give me? Well, whatever 1 minus cosine x is squared. And on the bottom I get 1 plus cosine x times 1 minus cosine x. First, outer inner cancel, and so I just have 1, what should it be?
Minus cosine squared.
There you go. Well, what's 1 minus cosine squared x?
Sine of x.
What is it?
Sine squared.
Sine squared. And now, check this out. Tangent squared equals two things that are squared. So, tan squared x over 2 equal to something squared over something squared.
Oh, take a square root of that.
Take a square root of that, and it turns out, this is the cool thing, is that, now, we're not going to prove this in class. We could prove this. I don't want to waste the time, quite frankly. It turns out that in this case, it works out that if one of them is plus, the other one will be plus. If one of them's minus, the other will be minus. You could check that if you'd like, but it is true that whenever this one's positive, so I took a square root, and that just leaves this. That just leaves this. And it does turn out that whenever one's positive, the other one's positive. Whenever one's negative, the other one is negative. So you don't need the plus or minus with that one. That's one of the cases where you could just do it. Again, I'm not going to prove that. You can. It's not too hard to do. You go through and you check a few things and go, oh yeah, whenever that one's positive, that one has to be positive. If that one's negative, that one has to be negative. We're not going to do that. But it's pretty cool to note. It's not too hard, actually, because if you look at it, 1 minus cosine at the smallest can be 0.
Oh, yeah.
Right? Because the biggest cosine ever is 1. So 1 minus 1 is 0. And then minus anything else is going to be positive. Right?
Yeah.
Because cosine shrinks down to 0. Well, 1 minus 0 is positive. Then when it's negative, like negative 1, 1 minus a negative is still positive. So the top's always positive. And then the bottom will be positive whenever sine is positive. And then you could go through and just say, oh yeah, and so whenever that one's positive, that one's positive. And you could go through with the half angle, and it works. It's just, I don't want to waste my time, or your time, or any of our time. And so, because I'm going to waste time doing this now, we could have done it this way, where you add the two. And what happens? Well, kind of the opposite thing. On the bottom now, we have 1 plus cosine quantity squared. And now what does the top turn into?
Wait.
When I multiply that times that.
1 minus, cosine of x. Outer and cancel.
Mm-hmm.
And then it's minus cosine squared.
There we go. Which is what? 1 minus cosine squared.
Sine of x.
Sine
Sine
squared.
squared.
And again, we're back in this bit where we have something squared is equal to something squared. And then you take a square root of both sides, right? Because what we have here is tan squared x over 2 is equal to sine squared x 1 minus cosine x quantity squared. So when you take a square root of both sides, you get tan x over 2 is equal to plus or minus the square root of that, which just turns out to be sine x 1 minus cosine x. But then it turns out that you can actually drop the plus or minus, because whenever one's positive, the other one's positive. Whenever one's negative, the other one's always negative. It does work out. And so, much easier with these guys. These are much, much simpler than having the square root of this thing, or the square root of this thing over the square root of that thing. Although, maybe that'll be helpful at some point. You never know when a trig identity will be helpful, but this is how it's in your book. This is how it's everywhere. These guys right here. Okay, questions? Before we move on. Okay. Alright, I wanted to do, let me check our time. Don't have too much time, so I guess I'll just do this one. So a lot of your homework is identities. And just bang your head against that. Good luck. Let's do this. So another part of your homework is find solutions that are in the interval 0 to 2 pi. And I wanted to do number 38. So, okay, I'm getting rid of all this. You good? Everybody good? Okay. Now I'll just say, the next quiz you have, we're going to have a lot of this stuff. I will permit you to make a note card. And you could put as many formulas on it as you want, like a 3x5 note card. You could put as many of these formulas as you want. And I will say, it is the act of making the note card is one of the best ways you could study. Because you have to sit there and think, okay, what do I want on this note card? Yeah. And you have to think, well, I only have this much space. So how am I going to organize this? And so, so already you're engaged with this stuff 2 different ways. Then you have to actually write it out. And then you watch yourself write it out. So you have all of these like modalities of seeing this information, organizing this information in your brain, then watching it being organized, and just the act of writing it out. Like I found that when I've had tests where you're allowed a note card, after writing the note card out, I rarely need to refer to it on the test because it's so well locked into my head. Because I've spent all this time planning, okay, what do I need? How do I want this organized? What's it going to look like? Then I have to sit there and write out the little things, and like doing that actually locks it into your head. So we're going to do that. And because you'll never remember all of these, except for the ones that I tell you to memorize, but you're certainly going to have a pop quiz. I'm going to tell you, hey, write this down. But yeah, so that's a common. Okay, so I wanted to do number 38, and this is find solutions that are in the interval 0 to 2 pi. Or solve on 0 to 2 pi. Okay? Cosine 2 theta minus tan theta equals 1. Any ideas?
Well, I think the formula. But we can't use one.
Minus the 1. No. Wait, so probably just get the cosine of 2 theta.
You could turn it into sine.
Into just in terms of cosine of theta, basically.
Okay, so say that again.
Get the cosine of 2 theta in terms of just cosines of theta, basically.
Okay, so cosine 2 theta is related to cosine theta how?
Well, we can just... It's like...
One way. I mean, there's a bunch of different ways, and this is part of this. This is what's so tricky about this. It's like there's a lot of different ways we could go here. One way is to say, well, cosine theta is related to cosine regular theta, but that would be this guy right here.
Yeah.
Right, so we could say, okay, right? I mean, that's how I have it in my head. You could do it the other way, where you have it as 1 plus cosine 2 theta is equal to 2 cosine squared theta. And so then cosine 2 theta is equal to 2, and this is one of those, that was one of the first ones we wrote on the board, so really we could have jumped straight there, but this is honestly how it's in my head. So, okay, so we could just say, okay, 2 cosine squared theta minus 1 minus tan theta equals 1. Now what?
Get the tangent in terms of sine, cosine.
Why not? Right? That's what I would do. I'm not sure. So let's try it. So I'm just going to rewrite it right here. I'm just going to erase and rewrite that as sine theta over cosine theta. So here's sine theta over cosine theta. Now what? Okay, I'm gonna jump in here. I'm gonna say, okay, let's at least get the numbers on one side and all the trig stuff on the other. I don't know if that's gonna help me. I don't know, but here we go. Let's just try. Maybe I've made my life harder. Maybe I've made it easier. I'm not sure, but I'm just gonna try. Why not? So let's get all of these. Bring the -1 over here. Now I have a 2. Okay. Okay.
Good. Oh, wait.
Well, we know what cosine squared is. 1/2 plus
Oh,
1/2.
we could get rid of the squared. Like
We could, and we're gonna, and if we do, but then now, here's one thing you got to keep in mind the whole time: is you probably could, from the very beginning, go one way or another way. But the idea is, as long as your variables are all the same. So notice this is a 1 theta, a 1 theta, and a 1 theta. If we go back then to 2 theta, now we have thetas, 1 thetas, and 2 thetas in the same equation.
Yeah.
Probably don't want to do that. I mean, maybe we do, maybe we don't. I'm not sure. But something tells me that's not going to be very helpful. You know, and this is just me talking here. I see a denominator. I don't know if this is going to help us or hurt us.
So multiply by cosine.
Let's try it. Let's see what happens. So how about 2 cosine cubed theta minus sine theta equal to 2 cosine theta. So everybody saw what I did. I just multiplied everybody through by cosine.
Now
Okay.
Minus the 2 cosine theta. To get it
You
all.
bring everybody over to that side.
And you can maybe factor it.
2 cosine cubed theta minus 2 cosine theta minus sine theta equals 0. Yeah, we could factor some stuff out.
A 2 cosine.
So 2 and a cosine come out. And again, I'm not sure. I'm just playing around, going with your suggestions here. And now what's left over? A cosine
Cosine squared minus 1.
minus 1.
Which is
Okay.
sine.
Good.
Is it sine
Oh, wait.
or? So wait, let's see.
Not
We know cosine squared plus sine squared is 1, and so then cosine squared minus 1 would be negative sine squared. So let's try that. 2 cosine negative sine squared minus sine. Okay. Check this out. Can we factor something else out? Because let's rewrite this. Sorry. 2 cosine theta. And you see what I did? I put them all together. There.
Yeah.
Right.
So now you can factor out that sine. Or negative sine.
I can factor out. Yeah, let's factor it out as a negative sign. So I factor out a negative sign, negative sine theta, and what's left over?
Cosine, 2 cosine of times sine.
Minus what?
Wait, wouldn't it be 2 cosine?
Well, I just, yeah.
Oh yeah, it doesn't matter.
Yeah, you see what I did, right? So I wrote them in the opposite order.
Yeah.
Maybe I'm trying to suggest something. I don't know.
Minus.
Now check this out. The reason why I wrote that instead of writing it as cosine sine is because earlier we had this on the board. Ooh. That's why I wrote it that way. It means the same thing, and now we can recognize that, right? Now here's the cool thing. We have something times something equal to 0.
Oh, so 2.
Yeah. You see, now we're doing all these different tricks and everything, and you're like, wait a minute. Like you could lose the forest for the trees here. You have an equation that's equal to 0, and it's something times something. So let's just jump to the chase here. and say, well, it's either the case that negative sine theta is equal to 0, or that 2 sine cosine minus 1 is equal to 0. Now, you're so used to saying, let's bring this guy over, and then we'll divide through by 2. But what is that? Like, this is something you'll have to keep all of these in mind. Like, the more you've written these things down, the quicker you'll go, wait a minute, that's a trig identity. That right there is the same thing as sine 2 theta. Right? So this is sine 2 theta. So on one hand, I'm going to say, okay, sine theta is equal to 0, because I just want to get rid of that. Now, that thing right there is sine 2 theta. Minus 1 equals 0.
So sine 2 theta equals
Sine 2 theta equals 1. Okay, so sine of theta equals... Now, just something to notice, right? Like I said, you're going to want to have all of your thetas and everything, and we don't want to mix our 2 thetas and our thetas, but then we ended up mixing our 2 thetas and our thetas, but that, back here, that wasn't going to help us, right? Like, that was going to make our lives more complicated. But once we got everything separated, right, we have something times something equal to 0, now you could go in different directions, right? So that's why you're going to do a bunch of these, because you're going to have to bend your brain in different ways and try a bunch of different things. And maybe you do a substitution that takes you far out in the left field. Well, just keep going. Like, you'll eventually get to something that will help you. So, okay. Sine theta is equal to 0 means that theta equals what? N times pi. Right? It could be 0, it could be pi, it could be 2 pi, and so on and so forth. Okay, so theta is equal to n pi, where n is an integer. Let's do this. How about sine x is equal to 1? That's an easy one. What I'm doing is I'm saying, well, let's let x equal 2 theta. So now, I'm going to use my best friends here. Okay, so
all the pi's over
that's
2.
the pi over 2, and then it has to be plus 2 pi, right?
Yeah.
Pi over 2 plus 2 pi, because that's how far that one is from that one, right? So this is 2 pi away. And so x would be pi over 2 plus 2 pi n. And it works in the opposite direction. I'm just going to check that with my thing that, yeah, the next time it comes back up, it's not after pi, it's after a full 2 pi have gone by. So it's in both the positive and the negative direction, okay? But we didn't care about x, we cared about 2 theta. So 2 theta is equal to pi over 2 plus 2 pi n. I divide everybody by 2, and I get theta is equal to pi over plus
Pi times.
there we go. And there you go. And that's all the time we have for today.